Imagine two marbles and we're going to collide them together. We've set up an accurate experimental apparatus to ensure that the collision occurs at the exact same spot with the exact same force each time. So far, so good. Now let's shrink these marbles down to the size of two protons. At this tiny scale, classical mechanics no longer applies. Instead, we enter the realm of quantum mechanics, where things get wonderfully weird. In quantum mechanics, every result we predict is a probability. We can't say with absolute certainty what will happen. Instead, we deal with likelihoods. Imagine the marbles are randomly vibrating as they roll along, causing fluctuations in our experiment. Each collision might occur at a slightly different point, leading to slightly different outcomes. So what happens when two protons collide? First, we have the elastic collision. Picture two billiard balls bouncing off each other. The protons bounce off each other, conserving both energy and momentum, but it gets more interesting with inelastic processes. Sometimes the protons stick together, forming a single particle. Energy and momentum are still conserved. Alternatively, a single particle might break apart into two particles. Again, energy and momentum remain conserved. Now let's venture into the hypothetical. Imagine that during a collision, the energy released is so immense that it triggers a phase transition, leading to the birth of a new universe. This universe could have different physical laws, dimensions, and even exotic particles we've never encountered. However, this remains purely speculative and unverified. If the collision energy surpasses a critical threshold, it might lead to the formation of a microscopic black hole. These mini black holes would evaporate due to Hawking radiation, leaving behind a burst of particles. But don't worry, they wouldn't gobble up our universe. High-energy collisions could produce exotic particles like magnetic monopoles, strangelets, or even dark matter candidates. Detecting these elusive particles would revolutionize our understanding of the cosmos. While the scenarios above sound intriguing, there are potential risks. Creating a new universe might destabilize our own, leading to cosmic chaos. If we accidentally create a stable black hole, it could wreak havoc. Exotic particles could interact unpredictably, altering fundamental constants or disrupting matter. Before diving into the mechanics of the Large Hadron Collider, let's take a moment to understand the building blocks of our universe, particles. These fundamental entities come in various forms, each playing a unique role in shaping the cosmos. First, we have baryons. Within this category, protons and neutrons stand out. Protons are positively charged particles residing in atomic nuclei. Each proton is composed of 3 quarks, 2 up quarks and 1 down quark, held together by gluons. Neutrons, on the other hand, are electrically neutral particles also found in atomic nuclei. They consist of 2 down quarks and 1 up quark. Next, let's explore leptons. Electrons, the negatively charged leptons, orbit atomic nuclei and are essential for chemical reactions and electricity. Then there are neutrinos, nearly massless, electrically neutral particles that interact weakly with matter. Neutrinos come in 3 flavors: electron neutrino, muon neutrino, and tau neutrino. Mesons and other hadrons add another layer of complexity. Mesons are composite particles made up of a quark and an antiquark. They exist only briefly, participating in strong nuclear interactions. Hyperons, heavier baryons containing strange quarks, are unstable and decay rapidly. Exotic particles like pentaquarks and tetraquarks further expand our understanding of particle physics. Pentaquarks consist of 5 quarks, including strange quarks, while tetraquarks contain 4 quarks, 2 quarks and 2 antiquarks. These particles challenge our conventional quark model and open new avenues for research. Now let's consider the charges in the universe. Interestingly, the universe appears electrically neutral overall. For every positively charged proton, there's a negatively charged electron. Neutrinos, being electrically neutral, don't contribute to the net charge. Charge conservation is a fundamental principle in particle interactions. The total electric charge remains constant, whether in particle collisions, nuclear reactions, or cosmic processes. This cosmic balance of positive and negative charges ensures stability. If the universe had a significant net charge, electromagnetic forces would dominate over gravity, altering cosmic structures. Understanding these particles and their interactions is crucial as we explore the vast expanse of our universe. With this foundational knowledge, we can better appreciate the groundbreaking experiments conducted at the Large Hadron Collider. Let's explore the colossal machine that makes such experiments possible, the Large Hadron Collider, or LHC. The LHC is the world's largest and most powerful particle accelerator. Imagine a 27-kilometer ring of superconducting magnets buried deep beneath the border of France and Switzerland. These magnets accelerate particles, usually protons, to speeds nearing that of light. Inside this massive ring, two high-energy particle beams travel in opposite directions through separate beam pipes. They are guided by an immensely strong magnetic field created by superconducting electromagnets. At 4 locations around the accelerator ring, these beams collide. These collision points correspond to the positions of 4 particle detectors: ATLAS, CMS, ALICE, and LHCb. Each detector serves a unique purpose, capturing the results of these collisions to answer fundamental questions about the universe. The LHC operates at an incredibly low temperature, colder than outer space, by chilling its magnets to -271.3 degrees Celsius using liquid helium. The particles within the LHC are so minuscule that making them collide is akin to firing 2 needles 10 kilometers apart with extreme precision. But what are the main experiments conducted at the LHC? ATLAS and CMS are like 2 detectives working on the same case from different angles. They study the standard model and search for new physics through proton collisions. Then there's ALICE, which specializes in heavy ion collisions, exploring the Quark-Gluon Plasma, the state of matter just after the Big Bang. LHCb focuses on flavor physics, studying B hadrons for asymmetries and CP violations. Other experiments like LHCf, Totem, Moodle, and Phaser each have their own unique missions, from simulating cosmic rays to hunting down rare cosmic creatures. Recent discoveries made by these experiments are equally fascinating. The LHCb collaboration recently observed a new kind of pentaquark, composed of a charm quark, a charm antiquark, an up quark, a down quark, and a strange quark. They also detected the first ever pair of tetraquarks, tightly bound combinations of 4 quarks. Beyond these discoveries, the LHC has unveiled a total of 59 new hadrons and counting, each contributing to our understanding of the universe's building blocks. The Large Hadron Collider is not just a marvel of engineering, it's a gateway to the unknown, pushing the boundaries of human knowledge. Let's dive into one of the most extraordinary states of matter. It helps us study the Quark-Gluon Plasma, or QGP. Quark-Gluon Plasma is an extraordinary state of matter that existed in the early moments of the universe, shortly after the Big Bang. Imagine a time when the universe was a cosmic pressure cooker, with temperatures and pressures so extreme that the usual rules of matter broke down. In this primordial soup, quarks and gluons, normally confined within protons and neutrons, roamed freely, unbound by the strong nuclear force. To recreate the conditions of the early universe, experimental physicists collide heavy ions such as gold or lead nuclei at facilities like the Large Hadron Collider. These collisions generate extremely high energy densities, briefly mimicking the extreme conditions that existed just microseconds after the Big Bang. In normal matter, quarks are the fundamental building blocks of hadrons, while gluons are the force carriers of the strong nuclear force known as quantum chromodynamics, or QCD. In the Quark-Gluon Plasma, however, these particles are deconfined and exist independently. This deconfinement allows scientists to study their behavior in ways that are impossible under normal conditions. But how do scientists detect and study this exotic form of matter? One method involves observing the particles that emerge from these high-energy collisions. The production of specific types of particles, such as heavy quarks or JP's mesons, indicates the presence of the plasma state. Another fundamental probe is the study of jets. High-energy quarks and gluons traverse the QGP, interacting with it as they evolve into a spray of partons. These partons eventually form hadrons, providing insights into the strong force and the QGP itself.